And what would n be for this hydrogen?
1.
And n plus 1 would be,
2.
and we call that splitting.
Doublet.
So what is the other good way to tell the difference between the spectroscopy for these two results?
Singlets versus doublets.
So if you get the printout from the computer and you see 2 singlets for the 1 integration peaks, then you know it's compound 2. But if you see 2 doublets for the peaks with an integration of 1, then you know it's compound 3. And that seems to be the method he was focusing on here in the exam, because that's what he gave in the example here. Both singlets, both doublets. Your method seems like it might work to me, though, because this does seem like this is closer to electronegatives than this one over here. However, there's so many electronegative elements here, it might be a little hard to make predictions based on that. In any case, just as a learning process, it's good to learn how we can use the splitting to distinguish between the different outputs. So now you can see that the splitting can be quite helpful in solving these types of problems. So remember, now we've seen 4 different types of information that might distinguish between the 2 printouts. One piece of information is the number of peaks, but that didn't help us here because we expected 3 peaks from both of these. Another piece of information is the chemical shifts, the horizontal distance, and you tried to use that to distinguish between these, and I think you were probably right. I think you were right that these hydrogens would be further to the left and those hydrogens would be further to the right, so I think that would be a good way to distinguish between these. Another way to distinguish is the integrations. Well, both of these would have a 3 to 1 to 1 integration, so that's not too helpful, but at least the integrations help us to make sure we know which peaks represent the benzene hydrogens. We would know that the peaks with an integration of 1 were representing the benzene hydrogens, and the peak with an integration of 3 would represent the methyl hydrogens here. And our fourth piece of information is the splitting, and that would definitely be very helpful here. That would give us a very clear-cut way of telling whether the printout came from compound 2 or compound 3, because here we would expect 2 singlets, and here we would expect 2 doublets. That make sense? Okay. That would be a good example to try again. Now remember I said that usually you only have splitting over a distance of 3 bonds or fewer. Sadly, in many cases in spectroscopy there's exceptions. So there's exceptions here for alkenes. You can have longer distance splitting across alkenes. Longer distance splitting across alkenes. You can have 4 bond and maybe even 5 bond splitting. So remember that in alkanes, we don't expect splitting over a distance of more than 3 bonds. 3 bonds between the hydrogens. 3 bonds between the hydrogens. But you might have splitting over 4 bonds or maybe even 5 bonds across an alkene. So for example, could these split each other? Well, how many bond distance is there?
4.
1, 2, 3, 4. So there definitely could be some splitting here. So what would we predict there? If we were going to take that splitting into account, what would n be for this hydrogen?
3.
And then n plus 1 would be
4.
And then what type of splitting is that?
Quartet.
Quartet. And let's do the same thing for the methyl group over here.
We have 1 equals 1, and then 1 equals 2.
And that's a
Doublet.
good. The best thing here is to actually draw out the bonds. I think we saw in that last example, it's easy to miscount the number of bonds if you don't draw them out. So if you're not sure, you should actually draw out the number of bonds. Again, how many bonds distance is there here between the hydrogens? 1, 2, 3, 4. Well, again, around an alkene, we can have 4 bond or maybe even 5 bond splitting. However, another complication, you would expect the 4 bond splitting to not be very pronounced because there's such a big distance, which would mean it has a small coupling constant. Remember, the coupling constant is how far apart the peaks are. Well, it's possible then that the coupling constant is so small that you might not be able to see the splitting on your printout. We've already seen that sometimes the printout doesn't match the theoretical predictions because you can't make out the fine details. Well, again, it might happen here that even though there might theoretically be a quartet here and a doublet here, it might be that, say, the doublet, the splitting for the doublet, the two peaks might be so close to each other. The two peaks might be so close to each other with such a small coupling constant, they just look like one peak. All right, so all we can say here is that theoretically, we could get a doublet and a quartet, and we may or may not be able to see that based on the coupling constants. So around an alkene, you can have 4 or maybe even 5 bond coupling. However, the 5 bond coupling, again, is so small that maybe we shouldn't worry about that too much. The 4 or 5 bond coupling would have a very small coupling constant. You might see 4 bond coupling, but again, it's going to be a smaller coupling constant than for 3 bond coupling. So you may or may not actually be able to make it out on your printout. So you have to be flexible when you're interpreting the printouts. They don't always match the theoretical predictions because there might be features that are there, but it's hard to make, there's not enough focus, so to speak, to see them on the printout there. For example, even in the example that we just did, remember we were doing this example, and we said that these two hydrogens should be singlets.
Right.
But actually, they're 1, 2, 3, 4, 5 bonds away from each other. So there might actually be a small amount of coupling between them. There might actually be a small amount of coupling between these two hydrogens. This was from compound 2. There might have been a small amount of coupling because they're 1, 2, 3, 4, 5 bonds away from each other. However, you would still be able to tell the difference between these because the coupling constant here would certainly be a lot smaller than when the hydrogens are only 3 bonds away from each other. So even if we don't get singlets here, we would get doublets with peaks very close to each other. Whereas here we would get doublets with a much bigger coupling constant. So we should still be able to tell the difference between them. Okay, but I wanted to warn you about that complication. All right, well, that's about as much time as we have. Unfortunately, you can see spectroscopy is a big subject. It kind of took the whole session just to kind of go over the basics, and we only had a chance to do a few practice problems. So what's important now is to try to find more practice problems. Unfortunately, there's only 1 or 2 other spectroscopy problems in this exam. Most of this is not about spectroscopy. So you have to go to some other sources for practice problems for this to really work on the spectroscopy skills. But we have gone over the most important ideas now. Like I said, you just have to keep in mind that sometimes the printout will not totally match the theoretical predictions that we've made. There are some complications that come up, and there's 1 or 2 complications we didn't have time to talk about. But we did talk about the most important features. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There is a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. By the way, I also offer tutoring via Skype, and you can find more information about that Skype tutoring service at my website. Thanks.